as it says on the slide, simplest terms, how fast work gets done, and you know what work is. It's how much force you apply to move something some distance. So power is the rate that you're doing that work at. Power equals work over delta T. We can break that out because we know this for work. We get power equals FD over delta T. And then we sometimes use this one. Your book gives that as power equals force times speed. Of course, we're more accustomed to saying velocity, but that's the way your book does it. And the one that we're going to use is, well, you'll see. So, if we were really doing this, you would want to put probably all three of those on your note card. They're useful. And I will say for your test, which we need to talk about when that's going to be, the conceptual concepts for power, I think, are fair game. I'm not going to give you workouts for power, but you should definitely know that power is the rate at which work is done. You should know the general equation for power. I just can't resist. What units? Okay, so the SI unit for power is the watt. What? Okay. I'll go home and do that to my husband all evening tonight. What? You need more power in your voice. I can't hear you. What? It's not actually funny, but this is what I do. So it's a joule per second. So if you can get 1 joule of work done every second, you are performing at 1 watt. Watts are really, really tiny. So this is kind of like, now, but it's I always want to say it's similar, Gesundheit, to the fact that we use kilograms, not grams, because grams are so tiny and so useless. And yet the SI unit for power is still, as far as I know, I would have to double check it, the watt, not the kilowatt. But we usually use the kilowatt because the watt is such a uselessly tiny thing. So 1 kilowatt would be how many joules per second? 1,000 joules per second. So 1 kilowatt would be 1,000 joules of work per second. Good? Okay. Where are you most familiar with kilowatts, kilowatt ratings? Yeah, electricity consumption. So you, and none of you are running your own households, I don't think. You're not opening your own utility bills and paying them yet. It'll come soon enough. Your electricity usage is billed in kilowatt hours. And once we get past the kilowatt, I always go all wrapped around the axle. But it's, in essence, how 1 kilowatt hour is using 1 kilowatt per hour, I believe. So it's like even another derived unit on top of the kilowatt. So you're not building straight kilowatts, you're building kilowatt hours. But, which probably opens some utility bills, but we're not gonna. Can't help myself. If you head out to Rogers on a Friday, somewhere you will find some crazy, wonderful little old man with a pile of small motors. They're all over the place. I love these guys, the crazy little small motor guys. And very often these are like, old blower motors from furnaces, just general. And if you're lucky enough to live the kind of life where you have a barn or shed or garage full of miscellaneous crap, you might have a few of these sitting around. And these small motors have, because this is, American, have their ratings given in not watts, but horsepower. And the common ones, like for furnace blower motors, so somewhere outside your furnace, you have a little motor that moves a little wheel that moves air up into your house. And typically those little furnace blower motors are like a 1/3 horsepower motor. So they can do, well, a horsepower is about 750 watts. So a 1/3 horsepower motor can do how many joules of work per second? Oh. I'll pause. In really round, rough numbers, yeah, 250 times 3 would be 7. Oh, it would be 750, wouldn't it? Okay, yeah, it's just 250. Okay. So 250 watts, which means 250 joules of work per second. Okay. If you have a 1 horsepower motor, you can do about 750 watts of work per second. These are small motors. I don't know. You can tear them apart. You can hook them to anything. You know, you can transform them into chicken pluckers. You can transform them into treadmills for your guinea pig. You can do anything you want with them. A 1 horsepower motor and a half horsepower motor and a 1/3 horsepower motor will eventually do the same amount of work. With enough time. It's going to take the motor with the lower power rating. So those stamps on the motor that say 1 horsepower, 1/2 horsepower, 1/8 horsepower would be a teeny little motor. Those are power ratings. And when you're looking at these things, one of them under load is going to go more slowly. You know. Now we never have, I would love to, maybe some year, we could get into a whole discussion about bogging down motors. I could have a whole little box of random motors that we could try to burn up. But the basics are, if you assume that the device does not fail due to overloading, they'll do the same amount of work. It's just going to take one of them a lot longer. I think it's pretty much common sense. There are probably some terms that you may not be familiar with. But a lot of you have some practical experience where you're familiar with work getting done. We talk about horsepower in an engine, in a car, or in a truck, or a bus. And the more horsepower, the more watts on the power rating in the vehicle, the more quickly it can do work. You know, in that case, typically the work is moving the vehicle under force. So a vehicle whose engine has a lower power rating has fewer horsepower. And yes, that does actually come from the fact that horses used to be the engines that powered our world. Sheer horse flesh. The car with the smaller power rating can accelerate less quickly. You know, all that. Okay, so this is sample problem 5F from page 188 in your book. 193 kilogram curtain needs to be raised 7.5 meters, which is a tall stage, in as close to 5 seconds as possible. Power ratings for 3 motors are listed as 1 kilowatt, 3.5 kilowatts, and 5.5 kilowatts. Which motor is best for the job? So, for instance, in the old building, we had the big overhead projector screen that came down in front of the auditorium. That had a small motor raising and lowering it, and it would be the same kind of calculation. You know, how quickly do you want this thing to go? What power do you need for it? So, if we know that power equals work divided by delta T, and we know that that is the force necessary times the distance that it's traveling divided by delta T, what force is necessary to just raise a curtain at a nice steady constant velocity? Give me a formula for that. If I am going to hold this here, what force is necessary to hold it? Mass times gravity? Because I'm overcoming gravity to hold it here. If I want to raise it at a constant velocity, what force is needed to do that? Okay, I'm out of space. Mass gravity. Because as long as it's constant velocity, there's no acceleration on it, and we want the curtain to raise in a nice, steady, stately fashion. I can't wait to see the play Friday night. I'm just thinking about it when I say curtains. So the force that's necessary is going to be the mass of the curtain times opposite of gravity. Because we have to, that's all we're doing. If we're raising it at a constant velocity, we just have to overcome gravity. Okay, so what we're solving for is just the power needed, and then we're going to match it to the pile of miscellaneous motors we've got. Okay, so we've got everything plugged in, and 193 kilogram curtain, opposing gravity 9.81 meters per second squared, moving 7.5 meters over the course of 5 seconds. Okay, so what do you get for a raw answer for power? You would like 2,839.995 watts of power. How many kilowatts is that? 2.8. So, of your options, what's the best motor to use? Well, if you had a 2.8, but you have a 1, a 3.5, and a 5. Yeah, the 3.5. So the 1 is going to be way too slow. The 5 kilowatt motor may like jerk the curtain up, and you can actually have, you know, a screen or a curtain tangle if you lift it too fast. So you'd want the 3.5. It might go a little bit faster than the 5 seconds that you're aiming for, but it's the best bet. So yeah, you need 2.8 kilowatts of power just to raise that curtain. Yeah, do you see what a tiny unit a watt is? Now, I mean, 193 kilogram curtain is not light. I mean, each of you is probably between 50 and 100 kilograms. So we're talking about a curtain that weighs as much as two of you. You know, this is, and stage curtains are heavy. So, questions, comments, concerns? You see the conceptual? It's really pretty stinking easy. We're not going to do any more work with it. That's it. You got time to work. Hand me your homework and I'll grade it the minute you've got it ready.